Welcome to the deep dive. Ever wonder how divers figure out, when it's safe to surface after being deep down breathing pressurized gas?
It's a critical question for safety.
Totally. So today we're getting into gas content algorithms. These are basically the brains behind predicting safe decompression.
That's right. There are mathematical models doing some heavy lifting.
And we've got some great sources covering the science, the math, applications, even some Spanish terms are in there.
You to mix.
Our mission really is to get you up to speed quickly on how these things work and, crucially, why they matter so much for diver safety. No getting lost in the weeds, just the key stuff.
Exactly. Let's unpack it.
Okay, so where does this all start? I read about John Scott Haldane back in 1908.
Yeah, Haldane. He was foundational. Before him, the thinking was simpler, but he proposed that our body isn't uniform.
Right, not just one big sponge.
Precisely. He suggested thinking about different theoretical tissue compartments. Some absorbing and releasing gas quickly, others very slowly. That was the key insight.
Ah, okay. And these gas content algorithms we're talking about, they're different from bubble algorithms, right? I saw that mentioned.
Good point. Yes, they are different. Gas content algorithms, like Haldane's original idea, focus on tracking the dissolved gas, mostly nitrogen or helium, in these theoretical tissues.
Okay.
They often lean towards allowing a faster initial ascent to help get that dissolved gas out efficiently.
And bubble algorithms.
They take a different tack. They try to model the actual formation and growth of bubbles. Often this leads to recommendations for deeper stops initially, try to manage the bubbles themselves. Two different philosophies, really.
Got it. So gas content algorithms are simulating this gas loading and unloading in these mathematical tissue zones. Zones, not actual, liver or muscle tissue.
Exactly. That's a common misconception. They're not mapping directly to specific organs. They're mathematical constructs representing areas with similar gas exchange speeds defined by their half-time.
Half-time. Okay, that sounds familiar. Like radioactive decay.
Precisely the same concept. It's the time it takes for a tissue compartment to get halfway to being fully saturated with a gas when you descend or halfway desaturated when you ascend.
And these times vary a lot.
Hugely. From maybe 4 or 5 minutes for fast tissues to over 600 minutes, that's 10 hours for very slow ones. Algorithms use a range of these, like the Bullman ZHL16 model uses 16 compartments. Some use fewer, like 9.
Okay, so going down is on-gassing, tissues soak up gas.
Yeah.
Coming up is off-gassing, they release it. There's an equation, right? The Bullman one. Looks kind of intense.
It does. P-comp, P-begin, plus P-gas, P-begin by 1, 2. But basically, P-comp is the pressure of inert gas in the compartment we're calculating.
Right.
P-begin is what it started at.
Yeah.
P-gas is the inert gas pressure you're breathing. And the 1 and 2 part, that just figures out how much it's changed based on the exposure time and the tissue's half-time.
So it predicts the gas load in each tissue type over time.
Exactly. And crucially, you can't just off-gas instantly. Ascent rate is critical. Go too fast, and the gas comes out of solution as bubbles. Decompression sickness.
Which is what we absolutely want to avoid. So algorithms limit how fast you can come up.
Correct. They impose ascent rate limits.
Yep.
And then there are M values.
M values. Maximum.
A maximum tolerated inert gas partial pressure. Think of it as the theoretical safety ceiling for gas pressure in each tissue compartment at a given depth.
Ah, so there's a limit and it changes with depth.
Precisely. It's not a fixed number. It generally decreases as the ambient pressure, PAM, decreases during ascent. There's a formula, Pigtol A plus PAM B, where A and B are derived from the tissue half-times. It shows the tolerance drops as you get shallower.
Okay, that makes sense. Less pressure outside means less pressure tolerated inside.
You got it.
And then gradient factors, or GFs, those are like adding extra safety margins.
Exactly. They let the diver choose to be more conservative than the raw M values would allow. A GF low, GF high, say 30-70, means you're forcing the algorithm to keep your tissue pressures further below the standard M values, especially deeper GF low and shallower GF high.
So 30-70 is more cautious than, say, 80-90.
Much more cautious, yes. It creates deeper and/or longer stops. It's interesting. Historically, people added deep stops, sometimes called pile stops. But some newer thinking, and the way GFs work, suggests that maybe very deep stops aren't always the most efficient. If your GF low is above maybe 55%, you might actually end up with shallower, possibly more effective stops compared to older models. It's still being researched.
Huh, interesting. So the algorithm calculates the ceiling, the shallowest depth you can safely go to.
Yes, the decompression ceiling. If the calculated gas pressure, P-comp, in any compartment exceeds its allowed limit, the M value adjusted by the GF, the algorithm says stop here.
And the tissue dictating that stop is the controlling compartment.
That's the one. And it can change during the ascent as different tissues off-gas at different rates.
Wow. Okay, so all this math is running inside a dive computer in real time.
Yep, constantly recalculating based on your depth and time. Computers are the most common application, but the same principles are used to create pre-printed decompression tables.
Right, the old school way.
And they're essential for managing repetitive dives, tracking that residual gas still in your tissues during your surface interval. Plus, they handle different gas mixes, like nitrox or trimix, by accounting for the partial pressures of nitrogen and helium specifically.
Makes sense. And you mentioned status terms.
Yeah, for wider understanding. Gas content algorithm could be algoritmo de contenido de gas or algoritmo de carga de gas. Halftime is often tiempo de vida media or semivida.
Good to know. So wrapping this up, the big takeaway is that these gas content algorithms, while complex under the hood, are fundamentally mathematical models helping divers manage their ascent safely by predicting how inert gases behave inside them.
Absolutely. They're a cornerstone of modern diving safety, translating complex physiology and physics into practical guidance.
Okay, so here's a final thought to chew on. We see these algorithms evolving, right? You mentioned hybrid models like the Suntafused RGBM2, combining elements of gas content and bubble approaches.
That's right. The field is definitely not static. Research continues.
So it makes you wonder, doesn't it? As we learn more, how might future decompression strategies change? How will we keep refining that balance between, getting out of the water efficiently and maximizing long-term safety? Something to ponder.
A very relevant question for the future of diving.
Indeed. Well, thanks for joining us for this deep dive.